to go. All right, so this is a special series on power series where we're going to be looking at power series. Again, how do we know a power series? How do we recognize a power series? It's got X in it. Yeah, there you go. There you go. And we've got to memorize for sine, cosine, and e to the x, right? Not just the pattern, but the general term as well. Just wash the blankets this weekend. Yeah, does it feel? Yeah, nice. Yeah, like probably gain maybe or down or something. Yeah. Geometric series. So to review geometric series here. If you start with like the first term of 1 and you let the ratio be 2/3, what would the series look like? Let's go ahead and write it out here. It would look like this, right? If the first term is 1 and r was 2/3, what would the next term be?
Oh, 5/3.
If r is 2/3. Remember, geometric is the exponential, right? It's multiplying. So all we have to do is keep multiplying by 2/3 to get the next term. So if the first term was 1, the next term would be 1 times 2/3, which is 2/3. And the next term would be 4/9, and the next term would be 8/27. Yeah, and because it's a series, you would add those together like that, plus dot, 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 right? And we would actually be able to write that any number of ways. We can write that with the general term showing, right? If you want, what would the general or the nth term look like to capture the pattern? It should just be what, 2/3 to the n, right? That would work, plus dot, dot, dot. You can then collapse it down, right, into sigma notation. And that would be from n equals something to infinity of 2/3 to the n. But remember, when you collapse it down, you need to make sure you capture the first term, which means we start at what? 0. Yeah, not 1, but 0. Good. And then there was another way to write it if it converged. Does this one converge? Yeah, this one does converge. It's not a power series. There's no x in it. It's just a convergent geometric series because the absolute value of r, which is 2/3, is less than 1. So we can actually write this another way. We can write it as what it's equal to. It's the first term, which is 1 over 1 minus r, right? And of course, that's equal to what? 3/3 minus 2/3 is 1/3. The reciprocal of a third is 3. So there you go. That's just another name for 3. So instead of 3 is a crowd, you could say sigma from n equals 0 to infinity of 2/3 to the n is a crowd, right? And people were like, oh, yeah. And yeah, I get what you're saying. Exactly the same. All right, what if the ratio now is negative 2/3 and the first term is still 1? What would that look like? 1, and the next one would be minus 2/3, and the next one would be plus 4/9, and then minus. Oh yeah. So that would be plus dot, dot, dot. So that's one way to write it. If we wanted to do the general term, what would that be? Negative 2/3 to the n plus dot, dot, dot. You could do it like that, right? Or you could even separate that, right? Because it is an alternating series. Negative 1 to the n times 2/3 to the n. Yeah, that would work too. You can collapse this down into sigma notation from n equals 0 to infinity of negative 2/3 to the n. And would this one converge as well? Yeah, it would have to be, right? Because it's smaller than the one above, isn't it? Yeah, heck yeah. So you could do like a comparison test, right? Since that one's smaller than the one above and the one above converges, this one converges too. Or you can also use the alternating series test. You can use the geometric series test, which would be the absolute value of negative 2/3 is positive 2/3, and it's strictly less than 1. And because it converges, we can actually write this as the first term 1 over 1 minus the r value. So we only take the absolute value of the r to compare it to 1, right? When we're actually doing the sum, we have to make sure it's negative, because now instead of subtracting, we're adding, which makes the denominator bigger, which makes the number smaller, right? Which it should be because we're subtracting every other term. So
Say it converges absolutely.
yeah, you can say it converges absolutely too if you wanted to, but it doesn't converge absolutely by the alternating series test, right? If you wanted to see if this thing converged absolutely, you would go back to A and say, hey, this guy without the alternator looks like that, and that guy converges by the geometric series test. Therefore, B converges absolutely. Okay, the alternating series test is not a test for absolute convergence. Okay, the ratio test is. So this would end up being what? 1 plus 2/3, right? Which is 5/3. And the reciprocal of 5/3 is 3/5. And is that less than 3? Yeah, yeah. Okay. So now what would it be if we do this? What if the first term is still 1, but we take the ratio and we just let a variable stand in for it, right? Your first term is 1. What's your next term?
X
Plus X. What's your next term?
squared.
Plus X squared. Your next one? Oh my gosh. Plus yada, 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 plus X to the N plus yada, 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 right? And if you were to collapse that down, that would be from N equals 0 again to infinity of just X to the N. Now that is a pretty easy looking power series to memorize, isn't it? 1 plus X squared plus X. It doesn't alternate. And there's no factorials. It's just like a polynomial that's being built up term at a time. Well, if this converges, there's another way to write it. What would the sum be? Well, it would be the first term all over 1 minus the ratio, which is X. And that's going to be for what values of X? For what values of X does this converge? What's that?
I just said something stupid. Never mind.
Well, no. Remember, if we're using the ratio test, the absolute value of X would have to be less than 1, right? And so that would mean that X would have to be less than 1 and greater than -1. That's how you can solve the absolute value inequality. You drop it and you get the right side, and then you put a -1 and less than there. So, and the endpoints will not work, right? We know by the ratio or by the geometric series test that the ratio has to be strictly less than 1. If you included the endpoints 1 and -1, you're going to get divergent. Okay, it's going to get 1 in one case and alternate in the other. So the endpoints cannot be included. For a geometric series test, endpoints are excluded. Okay, because remember, normally if you're trying to find the interval of convergence, which is kind of what we're doing here, and we use the ratio test, we have to test the endpoints separately. But if we can recognize what it is we're using as a geometric series, we don't have to test the endpoints. That's a time saver. So we'll say for -1 less than X less than 1, or you could say for X in the open interval from -1 to 1. That would be the interval of convergence. All right. Well, guess what? That is your last infinite series you have to memorize. 1 over 1 minus X. That's a rational function, right? It's actually a kind of a major transformation of the function 1 over X. But the function 1 over 1 minus X is what? I'm not going to look. If you expanded that out, it's 1 plus X squared plus X cubed plus X to the 4th plus blah, 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 X to the N, right? Yeah, so that's actually the easiest one to memorize. And it's equal to 1 over 1 minus X, okay? And this would be the Maclaurin series because it's centered at 0. Is that thunder? Nice. The thunder rolls. All right, so let's verify that by using a couple of things here. Part A says to use Taylor's rule. You want to do that? Let's try that. Okay, so here's part A. For Taylor's rule, our function now is 1 over 1 minus X. And remember, that's the same as the 0th derivative. And where's our center? 0. So now we want the 0th derivative at 0. I'm not going to put the 0th derivative. I don't really like the way that looks. Over 1 minus 0, which is what? 1. So that would be the numerator of the coefficient of the 0th term. All right, now we're going to need the derivative, f prime of x. Well, I don't want to have to hody-hi this thing all the time. So there's another version that I'm going to use for the derivative. and that's 1 minus x to the negative first. So let's just chain rule it, okay? The first derivative then is going to be negative 1 minus x to the negative second times the chain rule, another negative 1, which gives you negative 1 times negative 1. That gives you positive 1 all over 1 minus x to the second. And now, what's the first derivative at 0? Well, it's 1. I could keep going in this fashion, but you see already kind of how intensive it's going to be. The next one's going to be like a 2, and then so on and so forth. But if I wanted to, I can then say by Taylor's rule, so 1 over 1 minus x should equal, and we'll write the equation of the tangent line, which is the y value, which is 1, plus the slope, which is 1, times x minus the center, which is 0 to the first. And then the next one, I promise you, is going to be 2 over 2 factorial times x minus 0 to the second, plus so on and so forth. That would be Taylor's pattern, right? But if we clean that up and simplify, you would get 1 plus x plus 2 over 2 factorial. Well, that's going to be 1. So you get x squared. The next term, if you want to write it, is going to be 6 over 3 factorial, right? X minus 0 to the third. Well, that's going to simplify to just x to the third plus dot, dot, dot. And now you could pick up easily on the intrinsic pattern, yes? So if you needed to generate more terms, you're like, ah, okay. So that's one way to verify it. Let's verify it using part B. Using long division, okay? That one's kind of an interesting one, because if I have 1 over 1 minus x and you lean in real carefully, that little horizontal bar, you'll hear it say what? Divide me, divide me. You hear that?
Who wants it?
Yeah. Who wants it? So 1 goes on the inside, 1 minus x goes on the outside. And this is actually, when y'all first learn long division, or at least I wish your teacher would have shown you this, or at least when you learn division of polynomials, because it could have been like your first taste of infinity. Watch. We're going to write them in increasing order on the outside instead of decreasing order. How many times does 1 go into 1? It goes in 1 time. Now we distribute from on high and we get 1 minus x. And then we subtract, yeah? So we change both signs. And then we get x. And we do it again. How many times does 1 go into x? X amount of times. And now we distribute from on high and we get x times 1 is x minus x squared. Change both signs. So that's going to be minus plus. And then we get x squared. How many times does 1 go into x squared? So on and so forth. It goes x squared times, right? And if you keep going there, this is an infinite process. So you can already see that's plus dot, dot, dot. Okay, so there's a second way to verify it. And the third way is actually how we did. We just generated it using the rules of a geometric series. First term, and then x is your ratio. So what would be the interval of convergence for all of these? The interval of convergence, the IOC, or the domain is, again, we've already talked about -1 to 1, or x epsilon -1 to 1. No endpoints. And so this is why you want to recognize a geometric series as a slightly modified version of 1 over 1 minus x, because it saves you a lot of time from having to set up the ratio test just to get the interval or the radius of convergence, to then set up a possible interval and then have to come back and test both endpoints. We already seen how labor intensive that is. If you can recognize that as a geometric series, you know the endpoints aren't going to matter, right? Saves big time. Big time save. Big time save. Big time save. Okay. So what do I mean by recognizing something as a modified geometric series? Well, let me show you. Example 4, find a power series that represents the function x over 1 plus x centered at 0. Then find the interval of convergence. Include the first 4 non-zero terms in the general term. Well, if you're looking at that, you're like, that doesn't look like sine of x, cosine of x, or e to the x, does it? So you're like, man, I guess I'm just going to have to use Taylor's rule, right? I'm centering it at 0. The 0th derivative is the same as the function. which is x over 1 plus x. And so then the 0th derivative at the center, which is the same as f of 0, that's going to be 0. Okay, now I need the first derivative of x. Oh, crap, I have to ho-de-hi it now, right? Ho-de-hi minus hi-de-ho over ho-ho, and then plug in a 0. And then the second derivative, crap-a-moly. Now I'm going to have to clean that up, and then ho-de-hi it again. And then, wow, that's going to be pretty labor intensive, yeah? So maybe since it's a quotient, I can maybe build it from what I already have memorized. Can we build it? Well, let's see. The x in the top, I can factor outside. And that gives me this, right? And I know that one of the things I can do is multiply an existing series through by either a constant or a variable x, yeah? But that's still not quite what I have memorized, right? We memorized, oh, I jumped to example 4. Well, we're going to do example 4 or example 3 in example 4, because example 3 is asking us to find one for 1 over 1 plus x, and I already have one right here for 1 over 1 plus x. So let's just say it was by design. It's my way to kind of combine two problems into one. How would I write one then for 1 over 1 minus x when I have memorized 1 over 1 minus x? I could just write it as 1 over 1 minus what? Negative x. Ah, so now I know that I can figure this out because I can substitute in for x, a negative x, first, and then multiply through by x. So here's example 3. I know that 1 over 1 plus x, I'm just going to write it by itself, is equal to 1 over 1 minus negative x. And let's come up here for reference. Let's just write this down for reference. 1 over 1 minus x is 1 plus x squared plus x cubed plus dot, 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 plus x to the n plus dot, dot, dot. Okay, this is from my brain. Write it down. Now, again, because it did want the general term, let's just go ahead and write down x to the n and modify it as we go. So step 1, let's just substitute every x up here with a negative x, okay? And what is that going to look like? Well, the first term is still a 1, but now it's going to be minus x. What is the next term going to be? If I square a negative x, it'll be positive, right? And if I cube a negative, it's going to be negative. And I'll write one more term here. If I raise to a 4th power negative, it's going to be positive. So the degrees stay the same. It just becomes what type of series? An alternating series. So I can write that as negative x to the n if you want. You don't have to separate the alternator. Just plug it in as negative x. Okay, so that's example 3 right there. Easy, right? But now to pick up with example 4, all I got to do now to get the function I want is multiply through by an x. So let's go ahead and say, so x over 1 plus x should equal, and just imagine distributing an x all the way through there. If I distribute an x all the way through, it's going to be x now minus x squared plus x cubed minus x to the 4th plus x to the 5th plus yada, 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 yada. And again, notice I put plus, even though the next term would be minus. It's up to you if you want to do that. And then this is going to be x times negative x to the n plus dot, dot, dot. And there it is. I've technically got it done. Did I write the first 4 non-zero terms? 1, 2, 3. I wrote the first 5 non-zero terms. Is that okay? Yeah, you can always go beyond where it asks you to, but it has to be done correctly. And is that okay for the general term? Yeah, it certainly is. If it was a multiple choice question, that's probably not going to be what the general term looks like, but you've captured the pattern. If this were a multiple choice question, let's think about what they would do with the general term. You can't just add the exponents right now, can you? You can only add exponents when the bases are the same, and unfortunately, they're not quite the same. But I could do this. I can write negative x to the n as x to the n times negative 1 to the n, right? Separate the alternator from the magnitude part. And now I can add those together. So let me bring the alternator to the front, negative 1 to the n, and then it'll be times x to the n plus 1. That's a slightly better looking general term or nth term, rule of sequence, whatever you want to call it. Okay, so there you go. We did 2 problems in 1. And that's a lot faster than having to hody-hi it, isn't it? Using Taylor's rule. It would still work, but it would be it would look a lot messier before it would look any cleaner. All right. If you got the idea, try example 5 on your own. Find a power series for 1 over 1 minus x squared centered at 0. Again, find the first 4 non-zero terms and the general term. All right, quickly finishing up the previous question, because I didn't answer the last part, the interval of convergence. When you write it like this ends up being your R, right? Because you wrote it as 1 over 1 minus a quantity. So the absolute value of R would be the absolute value of negative x, which is the same as the absolute value of x, right? And that would have to be less than 1. And therefore, that still would give you an interval of convergence of -1 to 1. Can include the endpoint. Don't even have to test the endpoints. Okay. So it doesn't change the interval of convergence on that one. Now look on example 5. It's a quotient, right? It's 1 over 1 minus x squared. That looks a lot like 1 over 1 minus x. Let's go ahead and write 1 over 1 minus x down. 1 plus x squared plus x cubed plus yada, 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 plus x to the n plus yada, yada, yada. Well, what's the only difference between 1 over 1 minus x squared and 1 over 1 minus x? Yeah, there's an x squared there. Now, 1 minus x squared is not 1 minus x times 1 minus x. Okay, so I can substitute in. I can say 1 over 1 minus x squared. This would essentially be my R. And I just substitute in, right? So it's going to be 1 plus x squared plus x squared squared plus x squared cubed plus dot, 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 plus x squared to the n plus dot, dot, dot. We're substituting in now instead of a negative x, like we did on example 3 hybrid, we're just plugging in an x squared. And that actually kind of answers the question, right? We could simplify it though. And you get 1 plus x squared plus x to the 4th plus x to the 6th plus dot, 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 x to the 2n plus dot, dot, dot. So it's kind of cool again, if you want to, like during lunch or something, graph this in y1 with as many terms as you're comfortable with, and graph 1 minus x squared in y2, and you'll see that between -1 and 1, they're exactly the same. The more terms you add, the closer it'll look. Our function f of x isn't even defined at 1, if you notice that, right? It's not defined at 1 or -1. If I asked you to find the domain of that, you'd say 1 minus x squared can't equal 0. X cannot equal -1 and 1. It has vertical asymptotes there. So there's no way the endpoints can work, because a polynomial is not going to turn into a vertical asymptote. All right, but let me show you how you can find the interval of convergence. Because you know it's a modified geometric series, you would just say the absolute value of R, which is the absolute value of x squared, has to be less than 1. Well, how are you going to solve a quadratic inequality like that? Well, in order for x squared to be less than 1, x also has to be less than 1. Okay, and so that gives you the same interval of convergence. X is between -1 and 1. Okay, and then you got vertical asymptotes there. So it doesn't change. It doesn't change the endpoints. When might the endpoints change? Remember, only if we ever take the or the of the series, derivative or integral. Yeah, that's the only time the endpoints might change. We might gain them or we might lose them if we had them before. We never have them to begin with, though, when it's a modified geometric series. Okay. All right. So those are three examples, really, right? One where we replace x with -x, one where we did that first and then multiplied through by x, one where we replace x with x squared. Let's look at example 6. Beware a change in the radius. Look at this, example 6. Find a power series that represents 1 over 1 minus 2x. Yeah, that looks still like a quotient, right? I don't want to have to reinvent the wheel using Taylor's theorem. So if I just like put this in parentheses and call that R, that kind of looks like 1/1 minus a quantity, yes? So let's go ahead and write out for reference 1/1 minus x, which we know is 1 plus x squared plus x cubed plus yada, 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 plus x to the n plus yada, yada, yada. And now I'm going to replace x with what? 2x, okay? So 1/1 minus 2x is going to be 1 plus, I'll use parentheses here, 2x plus 2x squared plus 2x quantity cubed plus yada, 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 plus 2x parentheses to the n plus dot, dot, dot. And you've kind of met the minimum requirements there for writing that infinite series, that power series that represents that quotient. If you were to clean it up, let's see, that's 1 plus 2x plus 4x squared plus 8x cubed plus dot, 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 plus 2 to the n, x to the n plus dot, dot, dot. Okay. Now, the interval of convergence. The endpoints still are not going to work. But is it still from -1 to 1? No, because what's our R now? It's 2x. So the absolute value of R, which is the absolute value of 2x, has to be less than 1. Now that's a little bit different. Okay. So if you were to factor the 2 out, as long as it's positive, you can do that. And now how will I solve for the absolute value of x? All right, less than 1/2. Now, there's two ways you can interpret this. Because it's a geometric series, you could do like we did before. The interval of convergence is going to be drop the absolute values, x is less than 1/2, and then greater than -1/2. Or you can go back to what we did when we were finding interval of convergence. Your target is x minus the center less than r. Okay, and so if you wrote that, that would be the absolute value of x minus 0 is less than 1/2. And then what you would do is you come over here and draw the center at 0, and you would go plus 1/2 to 1/2, and then you'd go minus 1/2 to -1/2. And then normally, if we were doing it this way, we'd have to go back and manually test -1/2 and 1/2. Because it's a geometric series, we don't have to. Are they going to work or not work? We don't have to. They're not going to work, right? So the interval of convergence is, you could say x epsilon, strictly -1/2 to 1/2. All right. So either way, the geometric series is a time saver if you can recognize it, big time. And they will give you questions like that, whether it's a free response or multiple choice, where you're going to have to recognize it. So that one does change the center because we replaced x with a number times x. Okay. So lots of examples, very, very similar to each other, but now they're going to start getting a little more fun, just slightly more fun. Like example 7. I don't want you to get bored. Find a power series for g of x equals 1/4 plus x, centered at the 0 again. Okay. So notice these are all centered at 0 because that's the one we memorized. Well, remember, we have to make it look something like 1/1 minus something, right? Which is 1 plus that something plus the something squared plus the something cubed plus dot, 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 the something to the n. So let's go ahead and look at it. Well, I know that the plus x is not going to be a problem, right? Because I know I can write that as minus a -x, but the 4 in front of the plus sign, he's got to be a 1. How do I do that? Times 4? Oh, you pull a 4 out front. So factor it out. Yeah. So sometimes you do have to a little bit of manipulating. And that would be the first thing you would want to do. So in the bottom, factor out a 4, and that gives you 1 plus x fourths, or 1/4 x, right? That looks good. Now, I'm going to call that 1/4 times 1/1 minus what? -x fourths. Yeah. And that does the trick. Constant multiples, they never really matter, do they? They don't. They just go along for the ride in almost every aspect. All right. So now I think we got it. we have this part in here that's 1 over 1 minus an x value. So this is our radius, okay? So we can go ahead and start creating that then. Let's do, let's take care of the 1/4 at the end. Let's do the 1 over 1 plus x to the 4th. And we'll do that by writing everything up here. And in place of x, we'll put negative x/4. So it'll be 1 plus negative x over 4 plus negative x over 4 squared plus negative x over 4 cubed plus dot, 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 plus negative x over 4 to the n plus dot, dot, dot. Again, keep manipulating the general term or the nth term just like you do in the others. And let's simplify that. That turns into 1 minus x over 4 plus x squared over 16 minus x cubed over 64 plus dot, 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 plus, I don't know how you want to write this. Separate the alternator, maybe negative 1 to the n times x to the n all over 4 to the n. If you want to make it match the terms, that takes care of that. Are we done creating g of x then? No. Now I just need to come through with that and multiply everything through by what? 1/4, right? So now I can say, so g of x will equal, I can write 1 over 4 plus x if you want, but let's just go ahead and distribute a 1/4 all the way through. Okay, so imagine every single one of these terms with an extra 4 in the denominator. So that becomes 1/4 minus x over 16 plus x squared over 64 minus x cubed over 256 plus yada, 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 plus negative 1 to the n, x to the n, all over 4 to the what? N plus 1th power? Yeah, if I multiply by another 4 on the bottom, I can add the exponents. That's the fanciest looking general term. Okay, so there it is. That's a lot faster than using Taylor's rule. Okay, you memorize the geometric sequence or series, and then you can modify it. Now, if we want to find the interval of convergence, I could either A, do the ratio test on this without the alternator. Remember, the ratio test is test for absolute convergence. And then test the endpoints, yucky, yucky, gross, gross. Or I can say, oh, the 1/4 doesn't matter. This is just a modified geometric series where the endpoints don't matter. So the absolute value of r, which is the absolute value of x over 4, which is equal to x absolute value of x over 4, which is the absolute value of x all over positive 4. You could have skipped maybe that middle step. It has to be what? Less than 1. And now how do I solve for the absolute value of x? Multiply both sides by 4. And so I get the absolute value of x is less than 4. So remember, that's the same as x minus 0 is less than 4. So what's the radius of convergence?
4.
Yeah, the radius of convergence is 4. On the previous one, it was a half. Here, the radius of convergence is 4. And what's the interval of convergence? Good. Just negative 4 to 4, no endpoints included. Not going to happen. Ain't going to happen. It's geometric series. Time saver. So that one was kind of fun, right? It was kind of fun. Yeah. Sometimes, though, we cannot center our function at 0. In this case, we have to try and rewrite our function with the new center showing. Wow. Okay. Find a power series that represents 1 over x centered at 1. Then find the interval of convergence. Now, if we wanted to, could we just use Taylor's rule to generate the terms?
Yes.
Yeah, we can. We can't center this one at 0, though. Why not? It tells us not to, but even if you tried, yeah, it's undefined. So there's no way you can do that. No way you can do that. Now, you're probably not going to have to do something this fancy on the BC exam, where you have to rewrite that as a center C minus 1. So if I want the center to be at 1, then I'm going to need to have x minus 1 showing in my, I want to look for something like that, but it has to be equivalent. Is that equivalent right there to 1 over x? Because this is x minus the center. No, if you were to distribute that, you get 1 over 1 minus x plus 1. That ends up being what? 2 minus x. That's not 1 over x. So here's what we're going to do. We're going to start with the x minus 1 because that's the center. I have to have the center visible, and it always has to be x minus the center. Now, what did I essentially do? It's kind of like completing the square, but you're just completing the center. In the bottom, I really just subtracted 1, right? I'm allowed to add a clever form of 0, yes? So if there's a minus 1 there, I just have to add a 1 there. And now the denominator, if you simplify, is still 1 over x, yeah? Okay, and now to make it look geometric, that's going to be 1 over 1 minus what?
1 plus x.
Well, negative quantity x minus 1. Yes, yes? Yes, yes. Because we always have to make it 1 over 1 minus. 1 over 1 minus something. And now is that equal to 1 over x? Yes, it is. Okay, so how are we going to create that? Well, we're just going to go through, this whole thing is your r. We're going to go through the 1 over 1 minus x, and we're going to replace every x with the quantity negative x minus 1. You ready? This should be fun. 1 plus x squared plus x cubed plus yada, 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 plus x to the n plus yada, yada, yada. And what goes in there? Negative x minus 1, negative x minus 1, negative x minus 1, negative x minus 1. To do what? A finger twister then? Oh, okay. Yeah. Could be. Yeah. Now that kind of, that's the absolute minimum that you would need to do to get credit for that, right? If you simplified it, you would see though that it is also an alternating series. Let's see what that would look like. 1 minus. Now you don't want to distribute the negative here because remember, we like to have the center showing in our polynomial expansion. So x minus 1. When you square a negative, it becomes plus x minus 1 squared. You cube a negative, it's minus x minus 1 cubed, plus yada, 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 plus, and then you can separate it, negative 1 to the n times x minus 1 to the n plus yada, yada, yada. And now for the interval of convergence. The interval of convergence. I know that my r, the absolute value of r, which is the absolute value of negative x minus 1, which is the same as the absolute value of x minus 1, because I can get rid of that negative essentially. I know that that has to be less than 1. Okay, so what would the radius of convergence be? Remember, because the center's at 1 now, our goal, if you want to think about it, x minus c is less than r when the center is at 1.
Radius is still 1.
Yes, good. The radius is still 1. Radius equals 1.
Our interval of convergence is 0 to 2.
Ah, good. That's different. Your interval now is going to be from the center of 1, you go right 1, which is 2, and left 1 from 1, which is 0. And then endpoints are not going to be included. Okay, and you can do that one of two ways. You can either draw it. If the center is now at 1 and the radius is 1, you go plus 1 to 2, and you go minus 1 to 0, and then you get your 0 to 2. Or you could just say, oh, it's geometric. So the absolute value of x minus 1 is less than 1. How do we solve those? You drop the absolute values to get your first inequality. And then all you do is you put less than negative 1 on this side. And now you solve the compound inequality by adding 1 to both sides, or all 3 sides. And you get 0 is less than x is less than 2. And you know the endpoints are not going to work because it is geometric. Yeah. Now that's about, I mean, that's on the very edge of where BC might be. Okay, this is BC edge of the envelope. Okay, example 9 will not be, it's a bit of a booger. Go ahead and chew on example 9. You're going to be doing something similar to what we just did because you're going to write one that's centered at 1, but there's a little bit more beef in that one, a little more protein for you. Ethan's not even here.
Wait, he was like just here.
I don't know, but I changed his failing grade about 3 o'clock in the afternoon on Saturday. So,
Oh, we got a prom now.
yeah. Did he go to prom? Yeah. Okay, good. So he got the memo. I was trying to make him sweat a little bit.
If you fail, you can't go to prom.
Well, according to his dad, yeah.
Really?
Right. All right. All right. So 15 over 2x minus 1. I've got a quotient, and I'm trying to center it at 1. If you started using Taylor's rule, not that it would be horrible, but yeah, we're going to see if we can make this happen as a modified geometric series. So I know that the 15 is going to be factored out, right? That looks good. And then -1 plus 2x, right? We like to have the x term first. So that might be my first step right there. But what you want to do after you do that, before you start factoring out a 2 from everything, is get your center situated. The center has to be 1. So that's going to be 15 times 1 over -1 plus 2 times, and I'm going to do x minus 1 right there. Yeah, I'm going to create what I need. Now, to make that really effectively 0 in the bottom, if I were to expand that out, that would be a 2x, which is what I want, but it's also then a -2. So I really just subtracted 2 in the denominator. So in the denominator, I also have to do what? Add 2. So that's really just adding a clever form of 0. Okay? Adding a clever form of 0. Now let's see what that gives us here. That second term is 2 times x minus 1, but now I can combine the 2 remaining numbers, a -1 and a +2. What is 2 minus 1? +1. So now I'm back to 1 plus. That's looking a little better. All right. So now the 15's out front. I think all I have to really do is do 1 over 1 minus, and then brackets, -2 times x minus 1. Close, close, close. Does that do the trick? I think so. Because constant multiples out front, like, what are you guys doing in there? None of your business. We'll just multiply the final answer times 15. All right, so step 1, if we're going to create this, you don't want to create it necessarily in one fell swoop. Let's create it in 2 fell swoops, right? Let's just go ahead and replace, we'll replace x with -2x minus 1. And so we get 1 over 1 minus -2x minus 1. This is without the 15. I guess you could put the 15 and put a big bracket there, but it's going to be 1 plus x squared plus x cubed plus ... plus x to the n plus ... And again, notice how I'm doing that. I'm putting parentheses first, and then I'm going to come back and just put -2x minus 1, -2x minus 1, -2x minus 1, -2x minus 1. And then if you want to simplify that, you can multiply everything through by 15. You think you could finish it from there? Okay, I'm not going to finish it from there, but you get the idea. This one looks like it's also going to be another alternating series. But let's move on to the last part. Find the interval of convergence. Okay. Well, again, we're looking for x minus 1 to be less than r, since this is our center. Or we can just use the geometric series trick. So let's go ahead. That'll help us with your radius of convergence. So let's go ahead and take the r. This is what we would call r right there. Yes, -2 quantity. So the absolute value of r, which would be the absolute value of -2 quantity x minus 1, close, close. Oops. I could bring the -2 out as long as I make it positive. That's the same as +2 absolute value of x minus 1, and that has to now be less than 1. So how do I solve for the absolute value? I divide through by 2, and I get the absolute value of x minus 1 is less than 1/2. And guess what the radius is? The ROC then would equal 1/2. Yeah. And for the IOC, this is where you could do one of two things, right? You can either go to your center of one and add a half to get 3 halves and subtract a half to get minus a half, or you could do it purely algebraically, drop the absolute values to get your first inequality. And then all you got to do is keep the alligator pointing in the same direction and put a negative 1/2 over there. Okay, and then you just add 1 to all 3 sides, plus 1, plus 1, plus 1. And I'm going to scoot off over here. You get you get a half is less than x is less than 3 halves. So the interval of convergence would be x epsilon 1/2 to 3 halves. And do we need to test or include the endpoints? No and no, because it's geometric series. So it's a big time saver. Okay. Yeah, that one was good. Now we'll finish this on Wednesday. We got a couple things to do on 10 and 11 with integral and differentiation. We're going to work a practice AP question, and then we're going to look at evaluating power series at specific values of x. Okay.